Okay, so good afternoon, guys. My name is Samuel. I'm a data scientist here at CloudWalk. I'll be presenting a work that I did, that I'm currently doing on my master's at Federal University of Ouro Preto. Uh, so the main idea of my project is generate new features, automatically generate new features. So, because that is a problem that we currently have in many fields of data science. So, how we can generate new features and how we can see if this feature is performing well, and if the feature can perform well for a variety for multiple type of machine learning algorithms. So that's the main idea. Uh, so here we had an idea on the beginning. I think it's past. It has almost 2 years, 1 year and a half that I'm working with this. We start on this project for creating new features. We start to looking at convolutional networks, and that was a big problem for us because we work with tabular data. So we try some types of conversion. So we try to take the tabular data and transform it into an image, and then we apply a convolutional neural network to try to generate new features or even to be a end-to-end model. It didn't perform well because uh, there is some there's some problems when we are going to work with tabular data that we do not have when we are going to work with signals or images. That is the main focus of a convolutional neural network. For instance, a convolutional neural network assumes that there is a locality, a correlation between the members of between the inputs. So you assume that, and then we do the convolution, and convolution will extract the information on for a position and the neighborhoods. So this it is not always the case when we are going to work with tabular data, because if you have uh, a column like called time and then uh, amount, two columns, they may not be correlated. Uh, I think they probably will if you look closely, but uh, they may not be correlated. So that was a big problem. So, so first we have this feature generation workflow. So we have a data set, right? And this data set, normally what we do is that we send to a data scientist or a data analyst, and then they will just analyze the data, and then we extract the features, generate new features, and then they will add these new features to the data set, to the old data set, and then they are going to train the model. Of course, they can have a lot other steps on this process, but raw is this workflow. So the thing is that we have a lot of data. So the data analyst can work with a set of data, but each day we receive new data or new attributes, so or new features, and so it will reach a time that the data analyst will be overwhelmed with the data, and most in a lot of these new attributes, new features that was generated can be like missed on the analysis, because it's a lot of attributes and features to a person to deal with. Also, we have other problems, like we are biased. So our analysis can have the bias of the data analyst, of the So can im- this will impact the model uh, to work with the features that already is biased. So the other way that we can do this is using a automat AutoFE model. So automatic feature extraction. I don't know. I think it's this model. The name are just for run away from me right now. But what this model will do is just he will receive the data set and then he will apply automatically some transformations of the data, and then this will generate the new features. These have some advantages because like you'll not have any bias, right? Of course, it can have bias if your initial data already has bias, so it can have bias, but in the model itself doesn't have the bias, right? So if you have a data set without bias at all, so the feature that will be created will not have bias. But the thing is, these two can work together to also. So we have human features, the data analyst will keep creating new features, and then these new features can also be input to the AutoFE model. And then this can enhance our models. So uh, in the automated feature engineering, the name of just I'm working with this 1 year already, 1 year or more. The name just I forgot the name, but automated feature engineering. We can have some. The main principle is that we have some initial features, and then we are going to do some feature generations over these initial features. Uh, these feature generations, it can be is a set of transformations, right? So you can have some transformations that is already, you tell to the model which type of transformation that we have. So you can have log, max, mean. So your transformations will be met some mathematical functions, and then we are going to have a model that will learn the best transformations or the best combinations of this sequence, right? Because you have a sequence of transformations when you define the transformations that we are going to use. So if you have a max, min, which feature that we are going to be combined. So this is you have the sequence that you are going to apply the transformations over. Uh, but also we have other types where we take the transformations and then we apply a regression, for instance. And this will give us the results of that regression of these features, and then this will be our new features. Uh, we can also use multi-layer perceptron. In this case, it's a little bit more complicated because it's it will not give the best set of features most of the time. And then we have more using convolutional neural networks too. Uh, so that would be the transformations you have these transformations, or you have mathematical functions. In the end, all this will be using mathematical functions, but one will use like you have to explicitly tell which type of functions that we have, and the others we don't need to do that. And then we have these other transformations where we may not tell which type of transformations that are available for us to apply. So this would be the feature generation step, and this feature generation step will generate a lot of features, right? And to be honest, most of these features will be trash. Uh, and then you have to decrease these features the number of features that was generated. And then you are gonna you most of the models, most of the work was that researchers did on this subject, they apply a feature selection at the end. So they create a really numerous features. I don't know if, but there is a lot of features that is generated at the end, and then they're going to apply a feature selection. So now you have two big problems, right? Because the first problem is you have to generate a feature, and the second problem, you have to select the best set of features. So it's two problems, and we already know that selecting features is already a very complicated problem. So and generating new features is a way more complicated problem. So we have a really complex problem to deal with. Uh, so there is, for instance, when you use a convolutional neural network, there is the main topic of my work. Uh, we can kind of skip this feature selection process, but we do kind of have a feature selection problem in the model that I'm going to show later. Um, so we have a set of problems with this type of creations, right? We have manual feature, we can manual feature creations, we have limitations, right? It's limited to the knowledge of the data analyst, is limited to the, we have the bias of the data analyst. So also, when the amount of data increase, amount of features increase, it becomes a little bit more hard to work with. Also, it's kind of hard to extrapolate to complex features, because then you kind of have to look at correlations between several types of features. Uh, when we create new features, you can have we'll have a exponential feature space, because you are going to generate a lot more features than you have initially. So in this, if you have two features and apply two transformations, we are going to combine both of them. Now you have four, then you're going to have eight, and so on and so on and so on. So it's kind of, it's grow exponentially. Uh, we have limitations on the feature transformations when you are saying which transformations that it's available for your model. And we also have the limitation of deep neural network, right? So for instance, convolutional neural networks will not perform well working with tabular data. And if you use an MLP, you probably will not generate the best set of features for you. Um, So we have these two problems, the MLP and the CNN. The MLP, when you, with MLP, we will have these initial features, and then each hidden layer is doing a transformation on a set of features, right? So the thing is, uh, most of features will not have the same, uh, will not be correlated or have some information to when combined. So some connections should be zeroed, right? But learn this is not easy. Learn which type of connections should not be turned on, I don't know, active, it's not easy. So in the end, when you create this type of, you create these transformations, they are creating, you combine several features that may not have correlation with each other. And in the end, you have features that is not useful. Uh, and in the convolution, what we have is we are going to do this convolution, and what you can see is that the windows of the kernel he will be overlapping some other features, right? And but this feature here may not be correlated with this or with this, so it's kind of a mess here. And then we are assuming that it has a locality. There is a local uh, I don't know how to say it, but there is something that represents locally. So you have an image, and the image is it's white and it's turned to black, for instance. So it starts white and then got a little bit gray, and then it gets black. So there is this correlation, right? And this does not happen not does not happen, but may not happen with tabular data. So when you do this correlation, we are combining features that may not be useful together, right? And then when you go to the part of the dimensionality reduction, there would be the max pooling that is main use on this in this problem and in this type of layer of architecture. What's happening is that you are going to look at these two features that was extracted there, and what I am saying is that, well, the feature with the biggest value can express better this locality. That's what you're saying. But the thing is that these two features, when you are talking about tabular data, may not be not talking about the same thing, right? So you are selecting the max value between two features that may not be the same thing. For instance, could be amount and time. So it's not the same thing, and amount will be all can prevail, right? So it's not a good idea to apply max pooling when using this type of architecture with tabular data. So after that, uh, the common architecture is we pass this on the MLP, right? So we are going to pass on this new part that we call it global feature extraction, global feature creation, and this will generate the feature, but the feature is like we are going to generate the features with less uh, data, because here we are using all the features, right? So, and here we are not, here we decrease the amount of features that we are going to send to the MLP. So the chance of the features have correlations between each other is higher, but it's not always the case. So we have this type of problems when we are working also with convolution or with a CNN and the MLP. So the problem that we have with the MLP, we have also with the CNN, but is a little bit, there is not the same degree when you stop to thinking about because of the max pooling, or because of the pooling operation, it's better to say. So as I say, uh, this convolution will take the locality in will take the locality in consideration. So this local will be taken in consideration. So these features should have some degree of correlation with the feature on the site, but not is not the case when we are working with tabular data. So our architecture, it's we look at this problem and we just ask which part we can change to better work with tabular data. So we have this. We keep the architecture that is used on the literature, most of them. So we have this local feature extraction. There is basically the convolution and the pooling, and then we have the global feature generation that will be the MLP. And then what we do is just we add the new data, the new row on the data set, and then we are going to expand our data set to train the machine learning model. So the uh, the the thing that we changed was here on the pooling. So we thought we should use the pooling. We should look at the pooling in a way to work with tabular data. Max pooling will not be useful because of the way that he was built to work. He is not built to work with tabular data, right? He will not. It's work. It's the main focus is it's work signals, right? So we say, well, we can use correlation, right? And then we build the correlation pooling. And how you do this correlation is pretty simple. We compute the correlation at each row that we send to generate the new row for the new feature. right? So we send that row, and then and on the output, we have one value or two values or three values that will be the features that will be created for that row. So we concatenate that with the data set at the end. Uh, so when we pass these rows on the architecture, we compute the correlation at each row that is going, it's sent on the input, right? And what we do is just that on the last row, we update which features that will be selected, because we compute the correlation, the value of the correlation at the end. Uh, so each feature will have a correlation with a feature A will have correlation with all features until Z, right? And then we compute the average of this correlation, and this is the new correlation. Then what we do is just we select the best, the n best features with the highest correlation or the lowest correlation, you decide. And these will be the features that are going to be selected on the next epoch, because we use a evolutionary a genetic algorithm. So in the last epoch, we select the feature, these features. And so these features that select on the n, so the feature that is selected on Tn was computed on Tn minus one. So what we do is just we pass in the convolution, and then we do the correlation pooling. So we update the variable. This is we update the variable from R, that is the Pearson correlation. We check if there is the last row, right? And then we compute the correlation matrix for the average Pearson correlation for each feature. And then we're going to select the higher average, for instance. Uh, and then when you are doing this, on the pooling, on the process, right, the architecture that is not computing the pooling, so you still have the feature creation process, feature generation process. So we are going to just take the pooling of the car select features. So this would be the car select features from the previous epoch, right? And then we send this to the MLP, and then we compute the new features. So this is how we perform the correlation pooling. The thing that may be kind of confused is because we're using the past value to update the value from the future. But what we notice is that when the architecture is being trained, it reached a point that the modifications on the weights and the pooling and the features that has been selected for the pooling are so minimal that the architecture kind of normalize. So there is not a huge impact of doing this type of uh, of using previous data, previous info to update the current one. Uh, So this is just the feature evolution process. It's pretty simple. We have a we have a feature selection step to decrease the amount of features that we are going to send to the architecture, and also because we don't want to have features that has the same type of information or have the same that is redundant, right? We don't want that. So we just want the relevant features. So we'll do this feature selection step, and then we do the process of evolution, just generate a convolutional neural network, and then you go do the score, compute the score, and then the score in the end is computed using the new features. So you have the previous features with the new features. We do we put them together, and then we send to a machine learning model to score. And this is the score of our model, and it is what we want to optimize. And the feature evolution step, same thing as a genetic algorithm. We have a population, then we have a crossover and mutation we do over the weights. So we do crossover and mutation over the weights. And then the same idea, we do the score computation, and then we update or not the population at the end. Uh, so we have three research questions. The first was how effective is correlation pooling compared to max pooling, right? Then we have what's the impact of the number of data. And then because if you use all the data, maybe you don't need to use all the data, right? Maybe you don't. Because if you have a huge data set, then using the whole data to train the correlation, to find the correlation pooling, to train the correlation pooling, will transform your architecture in something that is not useful because it will take a lot of time. And then we look at the result of the proposed FeatGeNN, and we compare with the literature. So there's the experiment setup. We use F1 score and random forest. For the research question 1 and 3, we set a threshold for using only 80% of the available data and use also 5-fold cross-validation. So for the first question, we have this how effective is compared with max pooling. And then, as you can see, pardon. The proposed method is clearly better than the model that use max pooling. So this shows that Jesus Christ, this shows that using correlation pooling it's better to use correlation pooling when working with tabular data with convolutional neural network. So as you can see, we have, of course, there is not a huge, if you look at being really nitpicking, there is not a huge gain because we only work on the polling side, and I will talk a bit of this on the end. But to be able to have a better result, we have to find a way to do the convolution. But still, we have some improvements compared with the max pooling. When we look to the amount of data, you can see that this is the whole data. Okay, the model that use the whole data will clear will work better, right? And but there's some cases that you work with less data will give you a best performance. The thing is here is that you kind of can see that you don't need to work with all the data. You can use 80% of the data and you still have a good performance, and even using less because we use 100%, 80%, 60 and 30% of the data. So clear the 30% of the data is not good, right? It's too low, but from 60% or more, you can expect good results from the proposed method. And last but not least, how the model is compared with the literature. So here we have the max value, right? So as you can see, when compared with all the architectures, we have a huge leap, right? With the max pooling, we already had a huge leap, but when you compare with differ, for instance, there is state of the art, we had a really good results. Also, when compare, to be honest, we should just only look to the differ. There is the best one, and when compare with them, our proposed method is better. It's clearly better than the proposed method for Microsoft here. So yeah, we are on up something. So I think just keeping working a little bit more, we can find something that is that some great researchers let pass. But compared with literature, we also have competitive results, right? Uh, so now for future work, we are looking to the information theory to improve the pooling, right? Because correlation do not mean causation, so it's not very well. If you use a correlation pooling, it's not very good to be using. Of course, there is, because you are just looking to the linear relationship between two features. But yeah, so we are going to look at the information theory-based pooling and some advanced convolutional architecture in order to try to find the best way to work with tabular data, but on the convolution part. So the convolution part is the main focus right now, because if we can improve that, we can combine with the correlation pooling, we can kind of get something that is pretty interesting. So yeah, that's it. Thanks. Yeah, I talked too much. Yeah.
Really nice, Samuel. Really nice. Does anyone have any questions or comments for Samuel? Well, I think it's really, really, really nice, Samuel, your work. I think, yeah, you got state of the art, right? So you are into something. So how long are you into your masters? When did you start? Last year?
I started my master's last year, but I'm working with this, I think that is 1 year and a half or more.
Mhm.
So yeah.
Yeah. So you think what are the main limitations of your work? Actually, I think first, do you think like how, my first question would be like how do you think this can be applicable to other problems? And then like what's do you think maybe are the main limitations?
Okay. So first, the correlation pooling is the main goal, is the main gain here on my work, right? And it can be used not only for feature creation. It can be used in general. Uh, it just happens to be the scope of my research to be feature creation. So we can use for try to improve the usage of tabular data with convolutional neural network. Uh, Also, the main limitations is well, it take a little bit of time. So it's something that we have to work with. There is some research that uses that train the weights with several types of data sets, and then you just use your data sets, part of the data sets to fine tuning. It's kind of what they do with LLMs. And I think that's it would be a way to decrease the training time. Also, we have the problem with the convolution part. That is the one that we are addressing right now, because we have to find a way to do the convolution and take in considerations how the features relate to each other. So that is the main problem that is having the main limitation of the model.
Yeah, yeah, right. Because like if you have the compute, like the correlation is kind of it grows quadratically, right? With
Yeah.
the number of features, the number of features, not but the number of points on the data set. Yeah, but yeah, but still maybe up to a point is still doable, right? So you can apply this to different set of things.
Yeah, I think that it depends on the amount of data that you're going to send to the neural network, right? So if you're as the graph this shows, that I don't know how to go back here because I'm not very good on this. Okay, so if you look at here, we can decrease the amount of data, right? And then we still have a competitive result. So maybe still doable, but depend a lot. We have to, in this case, I think we, as all the other methods for feature generation, the thing is we have to train and see if the result, if the features that we generate, that was generated, can improve our problem, our model. So, and if it's doable, right? If it's because if you take too long to train, maybe it's not very useful, depending of the rate that you have to update your model.
Mhm.
So yeah, that's the downside. But I don't know. For to be honest, I think that my hope is that this just start a new way to look at tabular data and neural networks, and then more research comes on this from people that has a lot of more brain power than me, and then they are able to discover something great. Or if not, at least we did some research and show that, well, maybe it's not possible to keep on this way. So I don't know. Yeah, yeah. To be honest, it's just good to be doing research.
No,
So
but I mean, you beat the state of the art. That's cool. That's cool. But also maybe I don't know. Maybe like if you want to break down, maybe could do some parallelization, like on some smaller samples. I don't know. But I mean, there's lots of ideas that could be thought of, right? To
yeah,
do that.
right now, yeah, but right now we are kind of looking at convolution. The main idea that we had and we are going to try is is to compute, because since we compute on the pooling process, we compute the correlation, right? We can give to each feature, the feature A and the feature B has a correlation, and the feature C and the feature A has a correlation. We can maybe use this. So instead of, when we are going to do the convolution, we look to these scores between each features, and then we select the has the best, or they have the lowest. If you are going to look at the correlation, that you can select both of them. But you look at this, and then we combine just these features that has the same, that has the, for instance, the highest score. This would be a way to do the convolution. Of course, that you can discuss that the weights would be a problem, but you have to look at when you look at the convolution, you have to look at the weights as the transformation that you are going to apply, right? So the convolution is the transformation. So at each convolution, we are applying a transformation. So it's okay to have the same transformation for different type of combination of features. So maybe, and if this work, maybe this make the max pooling kind of useless for tabular data, because then we are not having this locality locality rule that the max pooling kind of needed, right? So the features had to be has to have a correlation between the neighbors. So when you use, if this type of convolution works, then this max pooling will not be useful anymore, and then the correlation pooling or the information theory based pooling would be the best choice. But we have to try, and I don't know, we are not trying, we are going to try right now, but it's not something that we are going to public, because if work with my doctor, so I don't want to lose this our work that is almost done. So yeah, but there is a lot of things to do. I think try to use G, graph convolution neural networks, or graph convolution networks, could be a way to work with this data. But yeah, I think there is a lot to do. I could be speaking this for forever and just on a monologue, because it's something that I really like to work with. But yeah, if anyone wants to help or want to try the model with the uh, CloudWalk data, just hit me up. I send the model, and then we can see what we get, right? But that's it.
Yeah, that's. Do you intend to do like a package, like
Yeah,
FS? Oh, nice.
yeah,
Nice. Um, yeah, really nice. And also, like, it was approved, right, for publication. Right?
yeah. It was approved for publication, and next year probably will be too. I hope.
Nice.
We have good results that is not on this paper. So yeah,
Yeah.
probably will be. So
You can choose where it's going. You're going to present.
yeah, I think we have something interesting. I don't know. I'm happy. Just I'm happy when the research payoff is it's interesting. Uh, okay.
Yeah, no, congratulations. Um, any other questions or comments for Samuel?